Okay, now that we've talked about atoms, we'll start looking at ions. This is section 2.6, ions and ionic compounds. I'll call this part 1 because I'm not going to cover in this discussion how to name compounds, ionic compounds, but we will go through the basics of ionic compounds, and we'll cover the chemical nomenclature, the naming of ionic compounds in a future video. So the number of protons in an atom doesn't change, but the atoms can, and they actually do, lose and gain electrons in chemical and physical processes all the time. In fact, inside your body there are reactions going on right now where atoms are gaining and losing electrons. Some of them are gaining, some of them are losing. That process occurs pretty readily in nature. Changing protons, because the protons are bound to the neutrons in the nucleus, it takes a lot of energy to remove them from an atom or to add them to an atom. So that does occur in stars, in our sun, through a process called fusion, and in some cases of radioactivity, such as the decay of uranium-238 or uranium-235. It can occur, and it does occur, but generally the number of protons in an atom doesn't change. In fact, because the type of atom is determined by the number of protons. So for example, uranium has 92 protons. If it were to lose protons or gain protons, then it would no longer be uranium. It would be a different element. So the number of protons in an atom doesn't change, so we don't have to worry about that. But we do have to worry about the changing of electrons, and that's our discussion of ions today. So a sodium atom is element number 11 on the periodic table. It has 11 protons, that's its atomic number, and it has 11 electrons. So notice same number of protons, same number of electrons. That means that all of the positive charge of the atom is perfectly balanced by the negative charge of the electrons. So we would write the symbol for this as Na, capital N, lowercase a. That's the symbol for sodium. So if we were to use a symbol to represent the sodium atom, we would use this. But in nature, it's often found that in fact, the sodium atom is relatively rare on the Earth. You're much more likely to find what's called a sodium ion. And a sodium ion has 11 protons, but only 10 electrons. So it has one fewer electrons than protons. That means it has more positive charge than it has negative charge, right? Plus 11 if each proton has a plus 1 charge, and negative 10 if each electron has a negative 1 charge. So that means it has a positive charge that's greater than the negative charge by 1. So we write that as Na+. You could also, if you wanted to, write that as Na plus 1 or Na 1 plus. That's indicating that this is not a sodium atom, it's a sodium ion. Here's another one found in nature. The chlorine atom has 17 protons. Again, this is the atomic number. It comes from the periodic table. 17 electrons, same number of electrons as protons. It's perfectly balanced. This is a chlorine atom, so we would write it as Cl, use the symbol from the periodic table. It turns out there's a chlorine ion, which has 17 protons and 18 electrons, and this is very commonly found. It's hard to see that negative, so I'm going to write it a little bit bigger, a little larger. Why negative? Because it has 18 negative charges, so negative 18. 17 positive charges, plus 17, so it has more negative charge than positive, so we write that as a negative. Okay. Here's another example. Barium. Barium is element number 56. Just look it up in the periodic table. So 56 protons. If it's an atom, that means it has the same number of electrons as protons. So 56 electrons, and it would have 0 net charge, so we would write it as Ba, just the symbol you get right out of the periodic table. A barium ion, I wouldn't expect you to know this yet, but we'll go over a way to figure that out, has 56 protons and 54 electrons. This is a common form of the barium ion. Now, let's figure out the charge. It has plus 56, that's in the nucleus, negative 54, that's the electrons, more positive charge than negative, so 2 plus. Notice that I wrote the number, then the charge. That's the most common form for writing the charge, is to write the number, then the sign, positive or negative, although quite frankly you could put plus 2 and that would be okay. So again, I wouldn't expect you to know that this is the common form of barium. We'll look at how to figure that out later. Some atoms can have more than one type of ion. Iron is an example of that. Iron has 26 protons, atomic number is 26, 26 electrons as an atom, Fe. The iron 2, now see this Roman numeral 2 here. The iron 2 ion has 26 protons and 24 electrons. So plus 26, negative 24, a net of plus 2 or 2 plus. So we would write the symbol as Fe 2 plus. But there's also a very common form of iron called iron 3. 26 protons, 23 electrons. Fe 3 plus. Why 3 plus? 3 more positive charges than negative, so positive charge plus 3. Okay, so there are different ions that can be formed. Now let's see if we can figure out some patterns to this. A lot of what we do in science is we look for patterns. And one of the patterns is, if you look at the periodic table, there's a tendency for the elements in the first column to have a charge of plus 1. Those are the most common forms of monatomic ions, one atom, one charge. Second column, plus 2. So how did I know barium was plus 2, 56? Because it was in the second column. If it's in the second column, that's the type of ion you would expect it to be. Coming over here, the noble gases. Noble gases don't tend to form ions, so they tend to have a charge of 0. They're neutral. Elements in this column 7a, that's right here, they have a tendency to be negative 1. Notice the exception to that's H-, well, it's not really an exception, but notice hydrogen sometimes is negative 1, sometimes is positive 1. That can happen. That's called a hydride ion right there. But F minus, Cl minus, Br minus, I minus, so negative 1. Next column over, negative 2, oxygen, sulfur, selenium, tellurium, negative 2. If it's in this column, which is column 6a, you would expect it to form an ion that's negative 2. Next column over, negative 3, nitrogen and phosphorus. Notice there's nothing over here, although sometimes people will put plus 4 and plus 3 over here. So for example, aluminum plus 3. Okay. Notice that in the middle here, the transition metals, the charges vary. So for example, Fe plus 2, Fe plus 3. Copper plus 1, copper plus 2. Gold plus 1, gold plus 3. Mercury plus 2. Mercury plus 1, mercury plus 2. So there's variations here. So we'll take a look at how that plays out in terms of our analysis. Now, the word nomenclature means naming. So we're going to learn a little bit about naming ions here. Not compounds yet, but ions. If there is more than one ion possible for an element, you use what are called Roman numeral system, or the stock system. So for example, Fe plus 2 and Fe plus 3 are both possible ions of iron. So if it's plus 2, we would write it iron 2 ion. Iron, and we use the Roman numeral for 2 ion. If you're not familiar with the Roman numeral system, it's pretty simple. And capital I is 1. 2 capital I's is 2. 3 capital I's is 3. Capital I, capital V is 4. Capital V is 5. Capital V, capital I is 6. And you can keep on going. Capital V, I is 7. V, I is 8. And then it becomes IX is 9, but you're not going to see these very often. X is 10. So probably the greatest number in this system you would ever see is probably 7, VII. Okay? So iron 2 ion, iron 3 ion. So we use the Roman numerals when it's possible that there's more than one formed. How do we know when it's possible? Generally, it's when they're in the transition metal range. So for example, magnesium, Mg+2. We might be tempted using this system to call it magnesium, oops, sorry, there's an S missing, magnesium 2 ion, but that would be incorrect because it's in the second column. If it's in the second column or the first column or somewhere over here, there's generally only one form possible. If there's only one form possible, you don't write the Roman numerals, you just call it ion, because we know that it's magnesium 2 because it's in this column. So any element here, +1, any element here, +2, -1, -2, -3, so forth and so on. The ambiguity is when it's in the middle. That's when we would use this system. Now, a little bit of terminology. Positively charged ions are called cat ions, like there's a kitty cat. Negatively charged ions are called anions, like negative ions, anions. Generally, metals form cat ions and nonmetals form anions. So if you take a look at the periodic table again, what you'll see is these are all metals over here, and they're all positively charged. These over here are nonmetals, and they're negatively charged. So you have to be a little bit careful. Some of these are metals. For example, tin, lead, and bismuth are metals, but the top part all the way over on the right, those are nonmetals. They tend to form anions. Of course, noble gases don't tend to form ions at all. Positive cations, negative anions. Anions, when we name them, we generally change the ending to IDE, pronounced ide. So for example, chlorine would be chloride. Oxygen would be oxide. So let me show you a few naming examples. Cu+, so we look and see where it is. Well, Cu is here in the transition metal, and so we're going to call it copper. And it's a transition metal, so it's going to use the Roman numeral system. Plus is just 1. So that would be called the copper 1 ion. Next one, Ni3+. Okay, let's take a look here. Ni is over here in the middle. That's a transition metal. So we're going to use the stock system, the Roman numeral system. So nickel. It's got a charge of 3, so 3. Ion. So this would be pronounced nickel 3 ion, and it is not generally considered correct form to use Arabic numbers, so we wouldn't write nickel with Arabic 3 here. We would want to use the Roman numeral 3. Ca+2, well, that's calcium, that's fine, and we know it's an ion, but do we use the Roman numeral system? Do we use the stock system? Calcium's over here, so no, it's not a transition metal, so we don't have to say calcium 2. We know it's 2 because it's in that second column. So it's just called the calcium ion. O2 negative, okay, well, we look for that. That's over here, O2 negative, right? Oxygen, but since it's negatively charged, we change the ending to IDE. So it becomes oxide ion. You could, in theory, call it the oxide anion, but there's no need to do that since it ends in IDE. We know it's an anion. N3 negative. Again, Roman numeral system is generally not used for the elements, the nonmetals. N3 minus is over here. So nitrogen is called nitride. Change the ending to IDE. So nitride ion. And some of the spellings, just so you have them, bromine becomes bromide, chlorine becomes chloride, fluorine becomes fluoride, hydrogen becomes hydride, iodine becomes iodide, nitrogen becomes nitride, oxygen becomes oxide, phosphorus becomes phosphide, and sulfur becomes sulfide. So I just picked probably the most common nonmetals there. Notice I did pick hydrogen, as again, hydrogen's an interesting element. It can form a cation if it's acting like a metal, and it can form an anion if it's behaving like a nonmetal. Okay. Now let's talk about polyatomic ions. we can have in nature clusters or combinations of atoms that are charged. So, for example, we might have 3 nitrogen atoms linked together, and the whole thing has a charge of -1. And that's called a polyatomic ion. In this case, it's an anion, negatively charged, because it has more than one atom. So a polyatomic ion is merely a charged particle that has more than one atom in it. So here's one right here. I'm going to name these for you. 3 nitrogen atoms with a negative charge. It doesn't mean that each one's -1. It means overall it's -1. This is called the Azide Ion. Here's one that has 2 atoms in it. It has a charge of +2. Mercury atoms. Hg is mercury. And so what happens here is these 2 atoms are linked together, and the whole thing has a charge of +2. That +2 charge is distributed through both atoms. This one is called Mercury One Ion. Interesting name, right? So mercury is, although technically it's not in the transition metal, it's a post-transition metal element. It does behave a lot like a transition metal. And when it has a charge of +1, they tend to cluster together as 2 atoms, and there's a +2 charge distributed through both. So the idea would be that each mercury has a charge of +1 on average. So if each is +1 and there's 2 of them, overall that would give you a charge of +2. Here's another one here, O2, 2 negative. This one is called the Peroxide Ion. Notice it ends in IDE. It's negatively charged. It's an anion. And that one, very simply, 2 oxygen atoms linked together. The whole thing has a charge of -2. Hydrogen peroxide, you've probably heard of. That's a form of the peroxide ion when it's bound with hydrogen. Next one. This one's a little different. This one has a charge of -1, but it has 1 oxygen, a different element here, 2 different elements. That's also possible. So an oxygen atom bound to a hydrogen atom, and again the whole thing is charged with -1. This is called the hydroxide ion. Very important ion. You'll use it a lot in your chemistry classes. Okay, so polyatomic ions can also possess atoms from different elements. Here's another example. 1 nitrogen, 3 oxygens. This one's interesting. It's called the nitrate ion. And it's essentially 3 oxygens that are bound to a central nitrogen. And again, the whole thing has a charge of -1. That's called the nitrate ion. Okay. Next one, NH4 plus, a nitrogen atom bound to 4 hydrogen atoms. Now this one, how is this one different from all the others? It's positively charged is the main difference. It has a charge of +1 there. Okay, so NO3 minus, OH minus, O2, 2 minus. This one's NH4 plus. This is called the Ammonium Ion. Again, another important ion in nature. And just to show you, it can get more complicated. I'm not really showing you very complicated ions. They can get much more complicated, but this one's a little bit more. This is called the Dichromate Ion. Di meaning 2. Notice this one ends in ATE, not IDE. The dichromate ion has 2 chromiums and then 7 oxygens and a charge of -2. So this one, I'll draw it for you. So 2 chromiums bridged by an oxygen, and then each chromium has 3 oxygens bound to it. So you get 7 oxygens and 2 chromiums, and the whole thing has a charge of -2. Okay, so just to show you, there are various different types of ions that can form. These are just a few. This adds a lot of richness to chemistry because instead of just dealing with elements, now we're dealing with combinations of atoms, different elements. Here from your textbook is a list of some important polyatomic ions. The list in table 2.3 is larger than this, but these are the 10 I want you to memorize. And when I say memorize, I mean memorize the name, the spelling, how you pronounce it, and then the formula, which should include the correct number of the correct symbols, correct number of atoms, and then the correct charge. So ammonium, 1 nitrogen, 4 hydrogens, and a positive charge, NH4 plus, ammonium. Hydronium, 3 hydrogens, 1 oxygen plus, H3O plus. Carbonate, these are all ions, CO3 negative, 2 negative. Cyanide, Cn negative. Hydroxide, OH negative. Nitrate, NO3 negative. Nitrite, NO2 negative. Phosphate, PO4 3 negative. Sulfate, SO4 2 negative. And sulfite, SO3 2 negative. These are the 10 that you want to memorize. Make sure that you're able to write their chemical formulas, we'll call these formulas here, from their names, and vice versa. If you know their name, you can find the formula, and if you know the formula, you can find the name. Other instructors in the future may require you to memorize more than those 10, but for this course, those are the 10. Now, let's put ions together, because remember in electricity, particles that have opposite charges experience a force of attraction or an energy of attraction. And since we have cations are positively charged, and anions are negatively charged, they will naturally form these small combinations, which we call ionic compounds. So let me show you an example. If we have 2 sodium ions, and they're both positively charged, and we bring about a negative oxide ion, right? The oxide ion, O2 negative, they will be attracted to each other, and they'll form what's called a compound in small combinations. And the driving force behind this, the reason for it, is that the positive ion is attracted to the negative ion, and vice versa. So they'll arrange themselves in a pattern in which the negative charge is completely balanced by the positive charge. So remember, atoms are neutral, ions are charged. Ions often form clusters in order to neutralize their electrical charge. So by having 2 sodium ions, each with a charge of +1, and 1 oxide ion with a charge of -2, the negative charge neutralizes the positive, right? +1, +1, -2. We have the same negative charge as the total positive charge. To make that happen, it takes 2 of the sodium ions and 1 of the oxide ions. If you want, you can put a 1 there just to remind yourself that's 1 oxide. What would happen here? Aluminum +3 and then chloride. This is a +3 charge, so we would need 3 of these -1 charges, and we would write that as Al. So whatever's over here, that's nothing written there, so it's assumed to be a 1, plus the next element, 3 of them, we would write that down here. So if it's Al1Cl3, generally we just write it as AlCl3. It's considered poor form to write Al1Cl3. It's not incorrect in a sense, it is 1. But if there's 1 of them, then we just don't put anything. So we would write it as AlCl3. Okay, now why 3 and 1? +3, -1. It takes 3 of those -1s to balance the +3. Suppose we have a +2 and a -2 here. Well, those are balanced already, so they could combine in just a 1-to-1 ratio. Right? +2, -2. It's already balanced. We don't need to have more than 1 of any of them. So smallest whole numbers. +2, -3. So nickel 2 phosphide. What would we do with this one? Well, if we did 2 of these, that would give us +4. That's more than -3. If we did 2 of these, that would be -6. Oh, but think about it this way. If I put 2 there, that would give us 2 times 3 is 6, -6. And if I put 3 here, 3 times 2 is 6. That's +6. That would balance. So 3 of these and 2 of those. So how do I figure that out? One way, a simple way, is to just go ahead and change the numbers, just to take whatever the number is here and write that over here, and whatever the number is here and write that number over there, and that will often work. So Ni3 P2. Okay? Now be careful when you do that method, because when you do that method, if we tried it with this one, we'd put 2 here because the 2 is there, and we'd put 2 here, and that would be incorrect. If you use that method and you get Fe2O2, just do one final step, which is look at these numbers down here. These are called subscripts, and if they're even numbers or they're numbers that you could divide by something and make them smaller whole numbers, then do that. So notice these are both divisible by 2. So if you divided them by 2, you'd get 1 and 1, so FeO. Again, we don't write the 1 there, but it's implied. And that would give you the correct answer. Okay, let's try another one here. +2, -2. Oh, they're already balanced. So Fe, CrO4. Now notice this one's a little more complicated. This is a polyatomic ion. This is called the chromate ion. So if there's only one of them, we don't need to do anything special. Fe is the positive, CrO4 is the negative. Again, 1 to 1. But look what happens with a polyatomic ion if the charges don't match up so nicely. Again, we said we could switch the numbers. So here's how you switch the numbers. Crisscross, sometimes that's called. You take the charge of the anion and write that as a subscript for the cation. So you take the 3 there and put it under the iron. And then you do the same thing for the anion. This PO4 is going to have the 2. But see what happens here? This looks like a 42. So if there's more than one of a polyatomic ion, we put parentheses around it. Okay, so PO4 2. And we have to be careful with our wording. Fe3 PO4 2 could be interpreted, if just from words, as being written in different ways. But the parentheses will be used to indicate there's more than one of the polyatomic ions. Okay, so practice some of these in section 2.6, and next up in our next video, what we'll do is we'll look at naming ionic compounds.